Welcome to the High Energy Density Science Seminar. I'm Federica Copari, research scientist at LLNL, and as chair of the HEDS Science Seminar Series, I'm pleased to introduce Professor Do-Kyung Ko as today's speaker. Professor Ko received a PhD degree in physics from Seoul National University in 1992. From 1992 to 2003, he worked at the Korea Atomic Energy Research Institute as senior principal researcher. Since 2003, he has been with Gwangju Institute of Science and Technology, GIST, as an associate full professor and served as the chair of department and the dean of the GIST College. Outside of the GIST, he served as the director of natural sciences at the National Research Foundation of Korea, and as the president of the Optical Society of Korea. Currently, he is the director of the Advanced Photonics Research Institute, which is affiliated institute of GIST. His research interests are nonlinear optics, nonlinear spectroscopy, and ultrafast laser development and applications. He published more than 200 peer-reviewed journal papers. And today, Professor Ko's talk is titled High Field Science Research at APRI-GIST, Korea. Before we start, I want to remind everybody that this talk is being recorded, and if you don't want to be recorded, feel free to leave the meeting. Also, it is an unclassified meeting open to external participants, so please be aware of export control issues. In-person participants, please wait until after the talk before asking questions, or at least until I pass the microphone to you so that online attendees can hear you. And remote participants, please type your questions in the chat, and I will read them for you at the end. And with that, I hope you'll enjoy today's talk. Professor Ko, please take it away.
Thanks, Federica, for kind introduction. My name is Do-Kyung Ko from Advanced Photonics Research Institute of Gwangju Institute of Science and Technology. And it's my great honor to be here to give a seminar lecture at Livermore, which is actually the top research institute in the laser field. Today, I'm going to talk about the high field science research of my institute. Yeah, this is content of my talk. Actually, I prepared almost 100 slides, so I'll start very fast, soon and fast. Maybe many of you know South Korea, but somebody might know much. So this is US, and South Korea is located far east of Asia. And Gwangju is located in the south of Korea. Okay? And this is the campus view of my institute, GIST. And here you can see 3 buildings, which is our research institute, APRI. And our Advanced Photonics Research Institute was established in 2001 as an affiliated research institute of GIST. And the mission is to promote science and technology through research on laser science and its applications. And the vision is, of course, to be a world-leading photon science research institute. So APRI was established in 2001. And after 2 years, we launched the ultra-short quantum beam laser facility project, which is about $60 billion for 9 years. And with this budget, we completed main building and completed ultra-short quantum beam facilities, and tried to make a big laser facility. And we got about 1 petawatt system around this 2010. And after that, we launched another one, IB Center, which is the Center for Relativistic Laser Science. It's a 10-year project. It's about $1 million for 10 years. And with this program, we increased the laser power up to 4 petawatt. And it is finished actually last year. And we now launched a new program. So we're going to continue to upgrade our laser system. So this is the organized. And actually, I am the director of this institute. We have 4 research divisions. And there are also 4 centers, which is based on the project. So if project is begin and center is born and finished, then it will be die. We have about 120 people, including IBS members, and we have administrative administrative step of 10. And I'm going to introduce shortly about our research divisions. First division is the division of ultra intense laser and application research. Here, they manage the laser facilities. We have two big laser systems, which is one is the multi-petawatt laser system. There are two beam lines. One is 1 petawatt, the other one is 4 petawatt. And second one is a little bit smaller. It's 150 terawatt. But the users are using more with these smaller laser systems. And they develop high power femtosecond lasers and ultra intense lasers. And they generate many high energy particle beams such as electrons, ions, and gamma rays, and so on with these ultra short high intense lasers. And research on the ultra intense laser matter interactions, also some computer simulations. And the other division is that division of applied photonic system research. They are making some applications with lasers. So they make some fiber lasers or solid state lasers for defense or some other industrial purposes. And also they are now doing some AI-based applied photonic systems. They control the laser beam shapes and the phases and so on, and also make some specialty optical fibers. And they also make some micro machining with femtosecond lasers, and make some devices with metal surfaces or photonic crystal fibers. And with these systems, they perform some terahertz spectroscopy also. And this division is more applied work for applied science and technology. So they transfer the technology in many fields, such as breathable films, or finder sensors, or multi-directional side-fire optical fiber tips, or some laser patterning for medical elements such as stent or implant, okay, and so on. And final division is that third division is the division of frontier photon research. They are doing some basic researches, and also some material-dependent researches like functional nanobioptoelectronic devices, photonic crystals, and some spectroscopy like this, cavity ring down spectroscopy, and so on. And they are doing some imagings and nanoplasmic materials and the biosensing platforms and the optical sensor for LiDAR. And the final one is the Space and Defense Convergence Research Division, which is built recently. So they making some lasers for space and defense science, and also for satellite orbit tracking and imaging for laser guided star. And they are doing some experimental demonstration for ground satellite laser communications. So recently we joined this one foundation, which is located in Switzerland in Jungfrau-Joch, and they are doing some research with Jungfrau-Joch and some Zimmerwald, which is more than 50 kilometers away, and they send the laser light, and they receive. So it's a kind of demonstration for ground satellite optical laser communication. So we joined as a member. So if you go there, then you can see our logo. All right. Now I'm going to talk about high field science research with our ultra-short quantum beam facility. First, I'll explain about the ultra-short quantum beam facilities. And this photo was taken about 21 years ago in Jeju Island. There are some big guys who were gathered in Korea. Maybe you know. This is Professor Morrow, Gerard Morrow, who is the Nobel laureate in 2018. And this Toshiki Tajima, he suggested about the laser wake field acceleration. And this is Chris Barty. He was a member of Livermore here. And these two guys are now in the UC Irvine as emeritus professor. And this is Peter Balco from Laboratory of Applied Optics for France. And this is Professor Jongmin, and this is me. And we took this photo by dreaming that to build very ultra high intensity lasers. And the backside, you can see some mountain. This is a kind of parasite volcano. It's very flat, very huge. So we dreamed to build petawatt lasers. This is optical table. So it was 2003, and we started ultrashort quantum beam facilities. At that time, we didn't know any knowledge about ultra high intensity lasers, but with help of those guys, we start to build. And this is the building. And the research goal of this building is to examine the physics of laser matter interactions under extreme conditions and develop cutting-edge technology in the field of ultra high intensity lasers. So this is the history of our facility. The project was started from 2003, but after 2 years, we achieved 100 terawatt beam line. And after some years, at 2010, we obtained 1 petawatt and the increased power. And after that, from 2012, new IBS project is started. So at the time, we tried to upgrade power. And 2016, we obtained 4 petawatt lasers. And 2021, we obtained more than 10 to 23 watt per square centimeter, which is the world best record until now. So this shows the laboratory layout. This is the original plan. This is the main laser room, which is where multi-petawatt laser system is located. And this is the experimental room for petawatt lasers. And this side is some experimental site for lower power, not low, but with just 150 terawatt, very low. So this is a photograph of main laser building. Laser started from here and divided into 2 parts. And this is 1 petawatt beam line. The other one is 4 petawatt beam line. This is a crystal. And this is small laser lab. Here we sectioned into 3 parts. And here's another small lasers, which is the homemade lasers is 150 terawatt lasers. And this is the petawatt laser plasma laboratories. So there are many experimental chambers. Okay. So here's the vacuum compressor, and we control the phase with deformable mirror chambers. And there are some plasma mirror chambers. I'm going to explain in detail later. And these are some how the target chambers look like. So this is the beam delivery and target chamber shape. The beam is come from here, and this is compressor, and divided into many parts. Okay, so we have many other chambers like this. And this shows the vacuum chambers for laser plasma experiment. And this is control room, which is located in the 2nd floor, and they monitor everything. And here they fire the laser light and get the data. And this is the layout of our 4 petawatt type titanium sapphire laser system. It starts from the oscillator, which is less than 10 femtosecond, and it's order of 10 nanojoule, something like that. And after 6 times amplification, we obtain 4 petawatt. So it's more than 10 billion times increase of power. Okay, this is how it looks like. Yeah, and this is the output energy and stability of final boost amplifier, this pump energy and this output energy. The efficiency is about 70%. So with about 160 joules, we obtain more than 100 joules. Okay. And the energy stability was 1.5% RMS, very stable, I think. And this is operated by 0.1 hertz. And this is how the first compressor look like. And we have 4 gratings. And this is first and fourth grating. The second and third grating is very huge, but it is very hard to make such a big gratings. And this grating was purchased from here, from Lawrence Livermore. I don't know what look like. Lawrence Livermore National Security, something like that. Okay, and we purchased from here, and it works very well. Without this grating, our laser system is not gonna operate. And this is the spectrum and the temporal profile. So bandwidth more than 100 nanometer, and the first duration was about 20 femtosecond. So we obtained 4.2 petawatt at 2017. And by using OPCPA, it's the optical parametric chopped pulse amplification techniques, we can extend bandwidth more and more shorter pulse. It's 17 femtosecond. And in order to clean the laser light, actually, oops. This is how pulse look like, but there are some pre-pulse, and because it's ultra high intense, even pre-pulse, which is very low compared with the main pulse, but still very high. So if this pre-pulse meets some matter, then interaction happens. Then we cannot perform the good experiment. So we should remove this pre-pulse. So one of the biggest one of the best ways to use the double plasma mirror. And when the pre-pulse hit the mirror, then this is a kind of dielectric and metals, and it creates some plasma. And then because plasma can observe at first time, but if plasma density is higher, then it reflects. So pre-pulse is observed, but the main pulse is reflected. So we can remove the pre-pulses. So after temporal contrast enhancement, we could enhance more than 700,000 times enhancement by using these double plasma mirrors. So contrast ratio is down to 10 to more than 10 to minus 17, something like that. Okay. So it was reported in 2020. So now we have very good laser facility and laser systems. So by using these lasers, we try to make higher intensity. So I'm going to talk about the record-breaking laser intensity. So this is the laser metal interaction on the laser intensity. As laser intensity increases, we can perform many experiments. But until gigawatt or petawatt, terawatt, we can achieve this power by using just a nanosecond laser. But beyond this intensity, we cannot do this, obtain more high intensity. But because due to the progress of intensity femtosecond laser technologies, we can increase the power. So many other research can be done by using femtosecond lasers. But if we obtain more than 10 to 18 watt per square centimeters, then the electron starts to move relativistically. So we call this region as a relativistic optics. So many research laser facilities are making systems so that they can obtain this area, 10 to 20 to 10 to 22. But now, and these laser systems can generate these exotic conditions like more than 10 to 20 watt. The electric field is more than 10 to 11 volt per centimeters. Pressure is more than gigabar, and so on. And our laser system is beyond this 10 to 23. Okay, so now I'll show how we obtain this. Before that time, this shows the evolution of laser intensity. So in the early 60s, twisting and modular King technology developed, and after that, there's no big increase. But after the development of chop pulse amplification by Gerard Mourou, and the power could be increased. And firstly, Lawrence Livermore here with Nova laser, they obtained more than petawatt laser system, and they could obtain 7 times 10 to 20 watt per square centimeter in 1999. This is the 20th centuries. And after that, Hercules laser in Michigan, they obtained a similar 10 to 22. And in Japan, J. Karen, and in China, Surf laser with 5 petawatt lasers, and Texas petawatt lasers, they all could obtain more than 10 to 22, but not more than 10 to 23. But in our institute, in 2021, we finally obtained more than 10 to 23 watts per square centimeters. So in order to increase the peak intensity, there are 3 ways to obtain high peak intensity. First one is to get higher energy. So we need more amplification. We need more power. Pump powers. So we need more money. So, and after that, we increase the energy with big money. But after that, we should do something else. So we should focus on the denominator, like time. We should decrease the time and decrease area. Then we can obtain more higher intensity. Okay? So this is what we should do. The first one is to make a good focusability. So if we have very good very good laser with very flat wavefront, then it will focus like this. It's perfect, but due to some distortion, like inhomogeneous gains or some thermal loadings and some distortion of optical components, then the wavefront will be distorted. Then if we focus, then beam is going to look like this. Then the focal size is increased. So we should compensate. So we should use adaptive optical systems. So this is how the adaptive optical system look like. Although we have aberrated wavefront, then here we locate some deformable mirror and monitor the wavefront and the feedback to the deformable mirror to compensate this phase. Okay? So we locate the 2 deformable mirrors. First one is before compressor, and another one is after the compressor. So first one is BIMOP deformable mirror with 48 electrode, and the other one is a bigger one with 127 electrode. So after that, we monitor the wavefront, and we could minimize some aberrations. So this is a comparison of Zernick coefficient before and after corrections. So we estimated the peak intensity, area, and the temperature shape, and finally we could obtain 1.4 times 10 to 23 watts per square centimeter. This is the world record. And it was published in Optica in 2021, and it was reported in physics.org. Okay, now we have very good laser beams. And with these laser beams, we start to experiment. So laser and matter interactions. So there are many large-scale conventional beam facilities like proton or heavy ion collide generator, like systems or electrons. This is synchrotron and X-ray, XPEL, or something like that. And this facility is a laser system. But if we can generate protons, ions, electrons, X-rays, then we can do everything with one facilities in tabletop scale. So this is what we want to make our facility. And with this facility, we performed these relativistic laser matter interactions to make a high energy particle acceleration with electron, proton, and ions, and also high energy photons, X-rays or gamma rays. And after that, we performed some strong field quantum electrodynamic research, like a nonlinear Compton scattering. So this shows how this interaction happens. Right. So first one is laser wake field acceleration, which is suggested by Toshiki Tajima in 1979. And if you shine the ultra-intense lasers to some gases, then the plasma generated, and the plasma wave is created. And due to the Ponderomotive force, electrons repelled, and they return to the backside. And if this electron is injected to this plasma wave, then due to the gradient of plasma waves, then electron can be accelerated. The electron can be injected or self-injected. We can inject outside from outside or injected by self. So this is how it looks like. And because it's like surfing, if you have a very high wake, then if you surf, then this surface can be accelerated. And this acceleration field is very high. It's more than 100 gigavolt per meter. So efficiency is very high. So this plasma accelerator is higher than 1,000 times higher gradient than conventional RF accelerators. So if we have these systems, we can use these electrons for next generation linear collider or high energy, high brightness photon sources, or even tabletop linear accelerator for other practical applications. Okay, so this can be a gateway for new physics. So I already showed this labs, and there are many labs. And here is the layout of petawatt experimental rooms. So this laser beam come from the laser room, and compress the laser light, and we use the deformable mirror, and the sender beam, and here, and this is a target chamber. Okay, so actually, already in 2008, with just 100 terawatt laser system, we already generate stable electrons to giga electron volt. So maximum intense was about 1 giga electron volt, and also about 300 mega electrons. This electron beam can be generated very stably. So we upgrade the system by using dual stage gas jet. First one is we use just only one gas jet, but it's too short. We use a 4 millimeter gas jet. So we used the two gas jets to increase the interaction length. So by this, first gas jet generates about 3 mega electron volt, and this injected to the second gas jet and increase more higher energies, accelerations. So with this system, we could generate more than 2 GeV electron beams. And also, we can control the phase of the laser systems to get higher or stable, more stable outputs. So by changing the chop, we could see that how the generated electron spectra is changing. And here we have another fix. That this is I think it's more than 2 GeV. Okay, so by using positive GeV and negative TOD, we could generate stable order of 2 giga electron volt electron beams. And this is the experiment by using some mixture, not only using helium, but here we put some other element. Helium is very light. It can ionize very easily. But if we put neon beams, neon is heavier atoms. So the plasma is created more higher energies. So we can control the energy and the plasma densities. And then we found that we could obtain higher electron beams. It's order of, we obtained the maximum 4.5 giga electron volt. So this is electron beam accelerations. And another experiment was to generate proton beams. So there are two kinds of mechanisms for generation of proton beams. One is RPA, it's the radiation pressure of accelerations. And there are two kinds of RPA, but here I'm going to introduce only one, light sail radiation pressure accelerations. Here we use very thin target. And if you irradiate ultra-intense laser light, because light itself has a radiation pressure, so this radiation pressure will gonna push this target. And so it looks like a boat, yacht. So this is the atoms. And if your laser pulse is irradiated, then electron is lighter than ions. So they are accelerate more easily. So like this sail, and the ions is behind. But because electron is already accelerated, they feel some electrostatic field like Coulomb force, so ion will gonna follow. So this electron and ions whole target will be accelerated in the simultaneously. So we call this as radiation pressure accelerations. And another one is a target normal shift acceleration. It's relatively thick. And if you irradiate the radio beams to this thin foil target, then in the front of a target, plasma is generated, and the electron is pushed out and go forward this way, and the electron is going out, and the protons behind this target, you're going to feel the electrostatic forces, and you're going to accelerate it. So this is generated normal to this target. So we call the target normal shift accelerations. So this is some experimental result by using polymer target with homemade thin target. We irradiate with about with 6 times 10 to 21 watt per square centimeters. We could obtain maximum 93 mega electron volt and proton beams. And another one is double layer target. Here we use the two mechanisms in the same time. RPA need higher intensity, but if you put another this is a near critical density forms this light, and if you shine the lasers, then this in this form TNSA model is applied, and the proton beam is accelerated. But after that, this beam is act like a seed, and they interact one more time in the thin foils, and then they can generate higher energy and high, more efficient outputs. So by using this double layer target, they obtained 48 mega electron volt with carbon ions, not proton, it's carbon. Okay. And also by using gold, we obtained more than 1.2 GeV by using this double layer target. And another one is just using TNSA model, but TNSA model is used relatively thick, but they obtain relatively lower proton beams than RPA. But if we decrease the size, then we can reduce the transverse current, and we can generate stronger longitudinal electric field. Then we can obtain higher proton beams. So by using 30 micron with polymer target, we could obtain more than 110 mega electron volt. And now this result is in revision in Nature Communications. I think it will be published very soon. Okay. So we call this target as a mass limited target. It's very small size. And another one is that now we could generate electrons and protons, and we started some other experiment, like quantum electrodynamics. also, because we have very strong field, we can perform the strong field quantum electrodynamics. So if we apply this strong field, then vacuum become unstable. So maybe this vacuum can be due to the, if you shine the photons, then vacuum can be destroyed and generate electrons and the positrons. And Schwinger, Professor Schwinger calculate the electric field for this phenomena. It at the time, for this phenomena, we need more than 10 to 16 volt per centimeters. We call this a Schwinger field. And if you recalculate into intensity, then we need more than 10 to 29 watt per square centimeters. But now we have just 10 to 23, still million times less than critical field. So we cannot perform this experiment. But if electron is accelerated, and if you interact with the accelerated electrons and photons, then Doppler effect happens. Then photon energy is increased very much. The frequencies increase. So then, because of this Doppler upshift, then we can perform similar experiment. So we use some parameters called the quantum nonlinearity parameters. Is defined as a laser light divided by Schwinger critical field. So if electron is at last, then we need this power 10 to 29. But if electron is accelerate, and if they have about 2.6 GeV, we could obtain this power electron beams. Then chi effect will be 1, and then we need 2 times 10 to 21. So now we have 10 to 23. So we can perform this experiment. So we start to experiment. So this shows a roadmap for strong field quantum electrodynamics. So as a function of chi, so if chi is 1, order 1, then we can perform 2 experiments. One is nonlinear Compton scattering, and the other one is Bright-Wheeler process. And if you increase more, then they can perform some more exotic experiment. But anyway, we are now here. The first one is nonlinear Compton scattering. Is electron and photons interact. But this is a nonlinear process. So not only interact with one photons, many photons will go interact with electrons. Then electron is scattered, and other photons with higher frequency. Here we obtain gamma rays, and this is a basic phenomenon in quantum electrodynamics. Other one is that gamma ray interacts with other lasers and generate electron and positron. This is creation of matter. This is a Bright-Wheeler process. Okay, so here is the it explains the nonlinear Compton scattering. Just Compton scattering is interaction with photons with electrons and scattered, and this photon lose the energy because of collision. Okay, this is very old story, but here electrons interact with many photons and generate other photons. This is a nonlinear process. Interacts with many photons. So we call this as nonlinear inverse Compton scattering or nonlinear Compton scattering. And another Bright-Wheeler process is gamma ray. Gamma rays interact with vacuums and create particles, positive and negative. This is just a Bright-Wheeler process. But if this photons is interact with other laser field, and some other nonlinear process happens, then maybe also positron and electron can be generated. So we didn't experience this yet. We did experiment only for nonlinear Compton scattering. So we we divide our light into two parts, and one laser will gonna generate electrons, high energy electrons, and the other electron is gonna interact with this electron, accelerate electrons, and monitor the output. Sorry. So main beam intensity 3 times 10 to 19, and it is going to generate, we obtain 3.5 GeV energy electrons. And the scattering beam is 4 times 10 to 20 watt per square centimeter. This A naught is about 14, and chi, I already told you the nonlinear value is around 0.5. So this is setup. Okay, we send the laser light, and there are some holes, and the main part goes to the some focusing optics with a long focus. This shines the helium cell and generates electrons, and other part is go around here and shine the electron beams as a scattering light, and we monitor the output, okay, by using scintillation crystal LISO and the pixelated LISO, and they obtain the shape and the energy spread. And this is the result. We generated more than 2.5 GeV electron beams, and this is output of photons. And if you plot, and here we could generate 470 mega electron volts gamma rays, which means that electron and 330 laser photons interact. This is the result. So this is published in Nature Photonics last year. And another one is to make vortex beams with ultra high intensity lasers. Most of lasers only spins, so the quantum number is 1 or -1. But if the light has orbital angular momentums, then another quantum number is called L. L can be any integers, because then we can extend the quantum numbers. Okay. So, so angular momentum can transfer from light to matter, so we can transfer the more energy or more quantum numbers. Okay. So we made the spiral phase mirror, and we used a small laser for this experiment, 150 terawatt, and we made some wavefront corrections. And here is how to look like a spiral phase mirror. Actually, it was made in Korea Basic Science Research Institute, and it was registered in US patent recently. And this shows how the generated light look like. This vortex beam has a 0 in center because phase is changing radially. So in the center, the phase cannot be determined. So there is some singularity in the center. So we obtained 1.8 times 10 to 20 watts per square centimeter. This is a highest intensity vortex beam up to now. Okay, this is what we have done in high field experiment, and we also doing some international collaborations. This photo shows many researchers, many big guys. Was taken in 2004 in Rutherford Appleton lab, and here's Toshiki Tajima, Muru, Hulin, and Chris Barty, Hutchinson, and so on. And we joined as a founding member in International Committee on Ultra High Intensity Lasers. It was a kickoff meeting. And now there are many ultra high intensity laser facilities in the world. And if you see, then many laser systems in the United States and in European countries and some Asia. Okay. So in Europe, there is a Laser Lab Europe program. There are 48 participants from 22 countries, and they help to access to many laser facilities around Europe and they organize some joint research and the networkings. And also in the United States, they have LaserNet US, and there are 6 universities and 3 national laboratories are attending, participating here. And the four is Colorado, Lawrence Berkeley, and here Lawrence Livermore and Jupiter, and the Ohio State, and the SLAC, Michigan, and Nebraska, Rochester, and Texas. So this program is supported under the DOE, I think. And in Asia, from 2004, we organized the Asian Intense Laser Network. Okay? And we also are the founding member of the Asian Intense Laser Network program. Still, some workshop is doing biannually. And in our institute, we made some Asian Laser Center program, which helps to collaborate among Asian countries and help the student to educate. So we are holding summer schools every year, every summer, until last year. It will continue. So I introduced about our research activities, and some research achievement with high field science is that we obtained more than 10 to 23 watt per square centimeters, and we would obtain 4.5 GeV electron beam, and ion generations by using several mechanisms, RPA, TNSA, and RPA plus TNSA, and we obtain like this. And mostly last year we performed some all-optical nonlinear Compton scattering. Nonlinear Compton scattering was already done in Lawrence Berkeley lab with high, more than GeV electrons, I think. But they use the synchrotrons, but this is all-optical. So this is first time to perform the all-optical nonlinear Compton scattering. We obtained 470 MeV, and with 2.5 GeV electrons, and with 330 laser photons. And I showed some international activities with high-intensity lasers. And we want to collaborate with many outstanding research institutes, especially with Lawrence Livermore. So I want you to have more interest on our research institute. Thank you very much.
Thank you very much. Such a nice overview of the capabilities of this facility. Thank you. Do we have questions in the room or online? There's a question online already, so let me read that for you. Question from Douglas. Wonderful talk, lots of content clearly described. Can you say a bit about the emittance of the wake field electrons?
Well, I cannot. Actually, I participated experiment until 2008, but after that, I didn't participate in this experiment, so I cannot remember the exact number, but no emittance. Here we cannot say just only some current here, only what 8 picocoulomb, something like that. For now, I cannot say the clear number. Sorry.
Thank you. Any other questions? Yeah.
So this is not about the details. Do you have any plan to make even higher power laser than 4 petawatt?
Yeah, actually, we we plan to make higher intensity because, you know, I used to check Eli beam lines. They already have 10 petawatt laser system, and in Shanghai they have 10 petawatt laser systems, and they are trying to increase. So Shanghai, they want to, now they are making 100 petawatt laser systems, and also Russia and the European countries already started to build. So we proposed the system to about 100 petawatt laser system to the government, and they lack of money, so we decrease the power. So we suggest about 40 petawatt laser systems and the plan, but it's actually now is, I mean, suspended or postponed due to some budget problem. And actually last year there's big decrease in R&D budget in our country. So now it's recovering. So, you know, there are some political issues in Korea nowadays. So if this problem solves, then maybe we can persuade. Actually, Gwangju and Naju is another city. The Gwangju means, you know, the Gwangju is the name of Gwangju means that the city of light. And there is another new university in Naju area. They want to build big facilities. So by helping each other, we want to make new systems. But I don't know. But anyway, we already suggest to the government that they know. So fortunately, hopefully, we want to make what 40 to 100 petawatt laser system very soon. Because now we have a very high intensity lasers, but now there are many other labs already have higher powers. So we are a little bit worrying.
Very nice talk. I keep wondering, as you were speaking, with these high intensity lasers, that must enable new experiments that are relevant to astrophysics.
Yes. Yeah.
And so, do you have anyone working on that, actually trying to reach, you know, gamma ray burst physics or black hole accretion disk physics, things like that?
Actually, I've shown many experimental results, but that was not done by ourselves. It was collaboration with other research groups. Some research was done with Chinese, some research with United States, and some is from European countries like UK and France. And they are suggesting some research on the astrophysics. And for example, nonlinear, I mean, strong field query experiment is, if we increase more, then we can access to some research for astrophysics. So that is one plan. So now new center program, new 10 years research program started from this year, and we are planning now. So maybe I think some research on the astrophysics will be included that experiment.
It'll probably help your motivation for, you know, enhancements to the facility, but it's also very good for science.
Yeah. But you know, Korea, we have a lack of researchers, so we need many help and collaboration with other research groups.
There's an opportunity there. I can see it.
Yeah. Please give many suggestions. Actually, this is a kind of user facility.
I'll tell you.
Yeah, please.
So at the end of your talk, a wonderful talk, congratulations. At the end of your talk, you showed some results with vortex beams at very high intensities, to look at quantum effects. So, what is the first experiment you would do with one of these vortex beams?
Well, we didn't expect that we could get such a big good result. And anyway, we found that we could apply, we could load, orbital angular momentum, so we can give more energy or more quantums to the matter. So now, still we don't have any concrete plan, but still we are thinking. But because this is ultra high intense, we are not using some quantum information or quantum calculation, but for the laser matter interactions, we can give some more efficient interactions than just with the spin. For example, proton beams, RPA, the light sail RPA model, we should use the circular polarized beam is better to make higher protons, but we don't know whether if we use the orbital angular momentum, then maybe it is going to help more efficient or more higher protons. So I'm not a theoretician, but if they suggest, then we can perform some experiment. And this fabrication is very difficult. With just 2 pi phase difference with this ultra high intense. So anyway, fabrication is difficult. Anyway, we succeeded.
Oh yeah.
Yeah. So for other experiments, for example, in order to make a larger orbital angular momentum, then we need more phase shift and so on. Yeah. And also this orbital angular momentum is just for the one fixed frequency. But this pet-out region has a broadband. So I don't know what can happen.
Yeah.
But anyway, we got some vortex beam.
Mingsheng Wei asks, do external users obtain access to your facility for experiments through an open call proposal process?
Yeah. I think new center is begin this year, and we're going to organize some committee for the research campaign. So we're going to announce. Then maybe you can suggest, you can propose project. Then there will be some screening committee. Then you can have some beam time. Actually, due to COVID-19 and other things, many experiments was not done. But I think last year maybe 4 or 5 times experiment campaigns happens, and we need about 2 weeks preparation period and about 2 weeks experiment and 2 weeks maintenance. So you need more than 1 month for each campaign. So not many, but anyway, about 4 or 5 experimental campaign can be done. So maybe we're going to announce later in the homepage or something like that, and maybe you can propose.
Yeah, very nice talk. And it seems like you achieved lots of progress in your scientific career.
Thank you.
My question is, do you have any primary scientific question that you want to reserve in the rest of your life?
My life?
Yes, yourself. What is your scientific goal?
For me, no. For me, no. But but we have new project leader this year, and he already suggests many new topics, including astrophysics, I think, and he will plan. And now we want to increase the power, but our interest is to make some nonlinear, QED experiment. So that will be one of the big challenging. So like, bright wheel experiment will be next step. So if we generally really create particles, electron and positron, antiparticles, then it will be a really good progress. That will be first. not for me.
Thank you. Any other questions in the room or online? If not, let's thank Professor.
Thank you
Correa.
very much.
Very nice
Thank
talk.
you very much.
Thank you everybody for attending. I hope we'll see you next time.
Thank you.